We start hocam.
Okay. Hello, everybody. This is like the fifth lecture of this dynamical system series. This will be like a general wrap-up of what we did. So I will do like, it will be a short lecture. It's kind of a goodbye lecture of the thing. And it was very nice to talk to you. I hope you enjoyed it. So I'll kind of start talking about what this is like, as I said, will be a wrap-up. So I'll start with what we wanted to do, what we did, what is missing, and maybe like spend 10, 20 minutes on how to fill what is missing, what you can do later. I'm not going to give much clue about what you can do later because we were chatting with your friends before this started. There are many directions where dynamical system leads to, from applications to absolutely theoretical math to fractional dynamical systems to discrete dynamical systems to stochastic systems and this and that. So you can be very pure mathematical, you can be totally towards application, and depending on what you really are interested in or what you need, you have extremely different directions. So I'm not going to recommend any particular book for further reading because it really depends on what you need. Anyway, let me start with sharing the screen. Okay, yeah. May I share the screen? Okay.
Now
No,
you can, I guess.
Okay, you have to let me.
Now you can, I guess.
Okay. Oh yeah, okay. Okay, so I'm sharing the screen now. You see the screen? Yes.
Yes, hocam, we can.
Okay, so let me see the screen myself in my computer too. Okay, so this was like our first page in lecture 1. This is the page I started with. And this was the plan: dynamical systems in 1 dimension, etc., autonomous equation, phase spaces, dynamical systems in the plane, linear equations in the plane, eigenvalues, fixed points, stability of fixed points, nonlinear systems in the plane, local behavior around fixed points. Now, we did all these 4, but then what we kind of thought we could do would be global behavior types of solutions, Lyapunov curves, and this very important Poincare Benedictine theorem for the plane, and some applications. So we haven't been able to do so. This, let me kind of put checks on this. These we have done. These we have not done. So today I really want to have like a short discussion of, no, I'm sorry, this is not what we haven't done. What we haven't done is these 2. Today I'm going to have a very short discussion of what I mean by these 2 and so on. So these 2 is like what we haven't done, and we're going to have, as I said, the excellent book is Dynamical Systems by Arrowsmith and Place. This is like, it starts with quite elementary ideas. Background is a little linear algebra and a little calculus, maybe a little advanced calculus, but calculus usually is enough. But with that, it really develops quite deeply and quite intuitively what dynamical systems are all about and how things work and so on. So it's an excellent system, and it's not really solving hard equations, but it's really soft approaches, geometric approaches, intuitive approaches, and so on. Mathematically, it doesn't contain all the proof, but it gives enough ideas that if you read the proof elsewhere, you can really understand the main points and so on. So this is what I wanted to do. So as I said, what I could not do is like global behavior, this Lyapunov curves and the Poincare Benedictine theorem. I'm going to very shortly, kind of discuss what they mean. So I'm starting with global behavior. So this global behavior is the following. What happens to the trajectories over long times. So say as t goes to infinity. What happens to the trajectories? Do they exist? Do they not exist? And so on. Now, remember, around fixed points, by linearization, we can answer this question. This question. We did that last week or the week before. We did that in the last lecture. We kind of, by linearization, we reduced everything to a linear system. And by looking at the solution of the linear system, we got the idea of what happens around near fixed points. So near or around fixed points. We can understand how the linear system, but in general, so this question is what happens in general. In general. And a very good tool, and this is related to the so-called energy methods. Now, a physical system has an energy. Say, suppose if the dynamical system represents some physical system, or chemical system or whatever system, if it represents some chemical system, example, like there are many F equals M, etc. Of course, you can write this as systems. I'm not going to describe it. Usually, it comes with, it will come with some energy. Some energy. Say E of T. And energy, what sort of thing is it? Well, energy could be like kinetic energy, potential energy, total energy. Say kinetic plus potential energy. And what we know with energy, what is really important is, the important thing is, usually energy is preserved or does not increase. It may decrease because you may be losing energy through friction or through some outside source and so on. But in general, energy is preserved, means, or does not increase, this means that E of T is the same as E of 0 for all T positive. So energy does not change. Energy is preserved. Now, usually E of T, E is just a function of X and Y. So E is just E of X and Y. Of course, everything depends on T. So E of T will be E of X of T and Y of T. You can think of X as the distance, position, and Y as the momentum, whatever. So you really have a lot of physics. Energy is a function of X and Y. So now comes the beautiful thing. For each constant C, that would be the starting energy. We could sketch the curve EXY equals C in the phase space. So what happens? Something like this. So EXY equals C would be some curve like this. No, I'm sorry, I don't want that. I want to draw this. This is the curve EXY. equals C, E0. But now what happens if solution should preserve energy, then x of t, y of t should be on this curve. This curve. So its solution should be like that. Now, usually this happens rarely, so we really know the trajectory. So this gives us the trajectory. Usually, we can only say that energy does not increase in time but may decrease as say with friction, etc. Due to friction, etc. Energy may decrease, then E of x of t, y of t will not be E0, but will be less than E0. This is the starting energy. This is E at time t. The energy will decrease. So this really says that, and this gives a bound on x of t, y of t. I'll give an example to what I say. It should be an easy example. Say, example, the most easy case. Suppose E of t is x of t squared plus y of t squared. So is non-increasing, but may decrease, What does it say? It really then says that x of t squared plus y of t squared is always less than E0. It cannot go beyond E0. So if you sketch the graph of this, you see initially we have a circle here. This is E equals E0. So that is x squared plus y squared equals E0. We have this graph. So it really, this means that x of t, y of t has to be inside. So the trajectory stays inside the circle for all times. So the trajectory should be something like this. You see, this gives an idea. So this is something like the global behavior. Means we can say something, about the trajectory. Okay, if it doesn't go out, then it has to stay in, and so on. Now, I'm going to give you another theorem. Now, in the beginning, I was mentioning two names, Lyapunov curves and the Poincare Benedictine theorem. So, Lyapunov curves generalizes this idea. They are curves, are usually closed curves, where the solutions, the trajectories, cannot cross, therefore always stay inside or always stay outside. So to make a picture, it's something, we have a picture like this. Now we have a Lyapunov curve, it doesn't have to be a circle, so this is some Lyapunov. Curve. It says that if the solution starts inside, it always stays inside. This is trajectory. Or if the solution starts outside, it never can come inside. So Lyapunov curve really gives an idea of how solutions are. So this is like a very good generalization. When you do applications, you use these a lot. And they're very good ways of finding how Lyapunov curves are, where they come from. Now, one other thing I wanted to talk about, again, this is in one word, the Poincare-Benedictine theorem is an essential tool for two-dimensional dynamical systems. It says this, it roughly says that if a trajectory, that is the curve x of t, y of t, stays within some bounded region, and the typical case is inside the Lyapunov curve. Then, as t goes to infinity, either x of t, y of t approaches a point AB, which is a fixed point of the system. So this is easy to see. So what we really have is we have a fixed point of the system here. This is my fixed point, and my solution kind of really approaches something like this. So this is like stable fixed point. Or it will approach some closed curve, which is also a trajectory and therefore periodic. Remember, closed curve trajectories were periodic solutions. So in this case, the picture is like that. I have a trajectory. This is like, say, I have a trajectory that should stay within this square. My trajectory doesn't really go out. So what can it do? Well, it can kind of come like this, come like this, come like this, but it has to approach something. It's not approaching a fixed point, but then what it does approach is something like this. There's a kind of like thing like this, a closed trajectory, and then it's approaching this one. You see, there's no way to move, so this approaches kind of, this is the picture of the so it's kind of going like this. Of course, it's not a very good picture, but what it does is approaching this red curve. And this red curve is itself a solution. Now, this is important because it gives us a way to talk about some periodic solutions without really computing them. Okay, but this is like, and then maybe important thing, this is false in R3, R4, and so on. Etc. It only holds on the plane. Why? Because in the plane there is not that much space to move. If you cannot get out of this basic rectangle, you don't really have much space to move. Whereas in the plane, in three space or higher dimensions, you can make curves, you can go in and out, and you get all these like strange pictures. Okay, so enough of this. Now I'm going to kind of talk a little about. Models. And so this is like my example, application example. And this is like, this applies to many things. That this is a standard example in like dynamical systems. This is called the Volterra-Lotka model. And it's two equations like this. These are the two equations. Equations of the model. So these are not linear, but quadratic, because you have xy terms. And these are quadratic, that's good. And then what you really see is, if we look at this now, dx dt is proportional to x. So let me just, the first equation says dx dt is proportional to x. So as x increases, dx dt increases, but is proportional to x. But inversely, it's not the correct, well, let me see. Dx dt increases as x increases, but decreases as y increases. Do you see? Because this minus is the term.
Hocam, there is a problem about sound. Is there a problem? I can't.
Yes. I guess your internet connection is not okay, hocam. I guess. But
we can't hear now.
1 second. Let me try to.
No, it is okay. No, it is okay.
Now it's fine. Okay.
Yeah.
Maybe I should get up.
Yes.
Okay, so roughly speaking, I'm saying roughly because you see you have AB minus plus and minus, but you see this now, this model is two competing species with population x and t and y of t, and the typical one is x of t are rabbits, y of t are foxes. What do I mean by rabbits and foxes? Well, foxes eat rabbits. So the more rabbits there are, the more foxes there would be because they have food. But the more foxes there are, the less rabbits there will be because rabbits will be killed by foxes. So you see that explains the sign plus here. So this is plus bx here term, and this is minus by term here. So more foxes means less rabbits because they eat them. But more rabbits means more foxes because they can grow, they eat better, they are better fed. So this is roughly the model. A, B, C, D are constants. Now with this model, I want to see what happens. So let me write this model, dx dt was equal to a minus by x, and then dy dt is equal to minus c plus dxy. And these a, b, c, d are positive constants in the model, depending on the physical. These are physical quantities, so they're physical constants. Now, what are the fixed points? This is quite an elementary computation, so I'll just do this. Maybe it will take 5 minutes. What are the fixed points? The fixed points is xy equals 0, 0. That's my first fixed point. And the second point is xy equals, well, it's not 0, 0, then x would be c over d, and y would be a over d. I have 2 fixed points. Okay, I have 2 fixed points. That's really good. So let me kind of have a little sketch. Okay. Okay, and physically, I'm only interested in the positive, in the first quadrant. So this is x. Okay, so this is my x. Okay. This is x, this is y. I'm only interested in x positive, y positive, because these are physical quantities. You cannot have negative number of foxes. But there's one fixed point here, okay? And one fixed point here, where is that? This is here. What was that? Y was a over b, and x was c over d. So this is the second fixed point. I have 2 fixed points. Now, if I look carefully, I see what is the sign of the x dt. Don't forget that x and y are always positive because they're physical quantities. Now, if x and y are positive, then dx dt is a minus by. So if y is bigger than a over b, here dx dt is negative, whereas here dx dt is positive. And if you look at dy dt, same thing, it is minus c plus dx. So here dy dt is positive, whereas here dy dt is negative. Okay, so we have basically 4 regions. In this region, x is increasing. So in the region, say this first region, so let's say in this region, dx dt is positive, dy dt is negative. Tells me, what does it tell me? It tells me that the curve, the trajectory moves down and to the right. Why? Because dy dt is negative, so it kind of goes down. But it moves to the right, so it should be like this. This should be the trajectory. If I apply the same logic to the other places, here dy dt is positive, dx dt is positive. So both x and y are increasing, so the trajectory is like that. Here, dx dt is negative, so x is decreasing. Trajectory is moving to the left, but dy dt is positive. So it's something like this. We have something like that. Now, if you look around 0, what happens here? Well, the trajectories are coming like this. You see, that kind of tells you that 0, 0 is an, so it looks as if, zero, 0 is unstable. Why? Because around 0, 0, the picture was like this. Around 0, 0, this was 0, 0, the picture was like that. And the other one, C over D, BA over B, is stable. Why was that? Because here, it seems that the trajectories are going around. So these are the trajectories. It seems that things are not that bad around that point. Now we can see this very easily by linearization. Now, I'm not going to do it. We can see this very, very easily by linearization. I'm not going to do it. I'm going to do it as an exercise. And I'll stop here. Why? Because what it says is like, physically, what does it say? There are two possible solutions, but let me say, physically, what does it mean? In terms of the model, this means two things. One, 0, 0, both populations may decrease to 0, may be 0, but this is unstable, so does not happen. Because one population may die, but the other one will not die. One population may die, only one population may die. The second one is, it seems that around the other one, well, it seems that this C over D and A over B is a stable fixed point. And there may be, I did not prove it, there may be some periodic closed trajectory. So the closed trajectory would be something like this. Let me use another color here. Let me use this green color. Here there could be a closed trajectory like this, which means a periodic solution. And what does it mean in terms of the populations? It means when one population increases, the other decreases in time. But after a while, the picture will be reversed and the foxes will decrease because there are not enough rabbits. And since the foxes decrease, the rabbits will increase. But once the rabbits reach a certain point, then foxes will start growing because there's enough food and so on. And this goes on forever and ever and ever. Of course, it really depends on the number, finding exact solutions, but really this gives you a very good way of, so this model may explain a lot of natural phenomena in terms of two competing species or economy models or this and that and so on. Okay, and I stop here. Let me say the end. And thank you for this. Thank you for following. This was like nice, a good experience for me. Okay, so if you have any questions, please go ahead, but I'm finished. Thank you for everything.
Thank you, hocam.
Okay, so I can stop sharing maybe? Yes.
Thank you
Okay.
so much.
Stop share.
Tamam hocam, yayını da kapattım. Hocam benim aklıma bir soru geldi.